Okay, so today we will be discussing artificial intelligence in design. Let me try to see. Yeah, everything is okay. And a lot of the work that is on these slides is created obviously by me, but some of the work is also created by my PhD student in the University of Antwerp, Eileen Visser-Similon, and also my former PhD student, Tanya Papasoteriou, who did a PhD in blockchain and urban governance in the University of Newcastle in Australia. Eileen is doing a PhD on the use of diffusion models in architectural design, and we'll see some of the work later. So this is kind of an introductory talk to AI for design. It's not for engineering, or it's not for other kind of aspects of artificial intelligence. And we will look essentially its development over the last 100 years. You might think that artificial intelligence is a very new subject, but actually it has been developing for a very long time, and we will see how these ideas kind of came to us from very early on in the 20th century. Does anybody recognize who the person on the photograph is? No? Have you ever used a 50-pound banknote? Well, you're a young generation, so you don't use paper money, yeah? Okay, we'll find out who he is. So I will start essentially with a great quote by one of my favorite books. This is a science fiction book, and it talks about planetary change. You probably have seen a movie in the last 2 or 3 years that came out. The book is called Dune, and the author is Frank Herbert. And he discusses essentially that once men turned their thinking over to machines in the hope that this would set them free, but that only permitted other men with machines to enslave them. So in the context of Dune, in the context of a planetary, essentially, change within the planet of Dune, Herbert creates a universe where computers, digital computers, and artificial intelligence is banned. It has become illegal to compute using a digital computer. Why? Because humanity essentially won a war against AI. So that kind of fear that people have, that AI is going to take over the world, and it comes actually from movies, right? I don't know how many of you know the Terminator series, which was kind of when I was young, it was one of the kind of best blockbuster movies, right? So AI becomes sentient, right? Kind of understands agency and starts to go against humanity. Or The Matrix, right? Which is another one where that kind of universe happens. But we will start essentially even before the 20th century. So this is Gottfried Leibniz. You might know the name from the invention, along with Newton, of calculus, which is the process in mathematics where we calculate differences in terms of very small numbers or very big numbers. He created essentially a machine that could manipulate symbols in order to determine the truth values of mathematical statements. Essentially a mechanical reckoner, a mechanical computer. When we say now a computer, we always mean something that runs digitally, right? Electronically, and uses digits, right? Uses 1 and 0, yeah? But you can also do the same thing analog with an analog or mechanical machine. But also it worked around the truth of mathematical statements, right? So does a particular equation, is it true or not, yeah? Does it work or not? And we move a little bit further in the beginning of the 20th century with Hilbert, one of the greatest mathematicians that ever lived, who was setting essentially a series of tasks for mathematics. They were trying to prove that mathematics is a complete science and is all-encompassing, right? And one of the problems they had is the Entscheidungs problem. Excuse me butchering the German, which is the decision-making problem, right? Can we build an algorithm, a process which, given a statement as inputs, answers yes or no? Can we build an algorithm that proves that this sentence is correct, right? So, and you'll see essentially that we run into a logical problem. If that is theorem A, and I tell you that theorem A states that it's a kind of circular argument, theorem A cannot prove this statement, so itself. If this is provable, if I can prove it with mathematics, it means that theorem A is inconsistent, yeah, because I'm stating it cannot prove itself. If it is unprovable, then it is incomplete. And immediately that small logic problem, I mean, I'm oversimplifying, the paper that Gert Gödel wrote about this was much more complex and used mathematics. It meant that mathematics is an incomplete science. And it is actually, in fact, human-made. Okay, so it's governed essentially by what we make as rules on that level. It's a very good one, it's a very, very, very efficient one, right? But it is actually incomplete because it cannot contain every source of truth within what it is being built without using an external system to reference it. Inspired by this conundrum, this person here, which was the person who you saw at the beginning, Alan Turing, created the Church Turing along with Alonzo Church, another great mathematician of the 20th century, the thesis on commutability. And to do that, he used what is now called, to his honor, a Turing machine, which was essentially a mental experiment, right? So he thought about, let's say I have a machine that could actually, that I could use the machine to either go with proving that something is inconsistent or proving that something is incomplete. So he was able to show that we cannot really use a machine to do that. And even if we come close, there was always going to be the problem that some statements are unprovable. But in the process, he invented essentially the concept of the computer, the digital computer, which is what you use most of the time right now. So a Turing machine is essentially a tape of infinite length where you can have essentially boxes, and in those boxes you can read from them or you can write to them, and you have a set of rules that drive the computation that you will do. Okay, so the tape is memory, the set of rules is the software, and the actual reading or writing is the processing unit, if you will, right? I'm oversimplifying, but essentially he invented the idea of computation through a set of instructions, right? And within that, he was also able to create essentially one of the most important questions within artificial intelligence, right? Can machines think? I mean, they can do a lot of stuff, right? Can they think? Does artificial intelligence, when you use it on the web, actually thinks? Or does it do something else that looks like it? Is it enough to actually look like it, emulate it, or do you actually have to do it? What is the difference between simulating thinking and actually doing it? I don't expect you to have an answer to this. I expect you to kind of think about it. Yeah. So he developed what is called the imitation game. And this should begin with definitions of the meaning of the terms machine. What is a machine? And what do we mean when we say think? And he kind of created a Turing test, which was this case. He said, we will put you as a human in a test where you're going to be in another room and your judges are going to be on the other, and you're going to have a conversation. And you need to convince the judges that you are human. If at the same time we put a machine to the test and the machine convinces the judges that the machine is human, then they have passed the Turing test. The machine has imitated a human. Okay? So you're in another room, you don't know whether the person on the other line is actually a machine or a human, right? And you're trying to have a conversation, right? What kind of questions would you ask it to find out if it's human or not? Anyone? How do you feel? Very good. Any other question? Have you eaten? Very good. What have you eaten? Or what's your favorite food? Any other question?
What's your favorite song?
What's your favorite song?
What do you like to do in your pastime?
On your free time, what do you like to do? Yeah. So, do you, what's your favorite memory from your childhood? You see, these are all things that potentially, if you combine them, it makes us human, right? And kind of work as a kind of common base between us, okay? Nobody went with, can you solve this equation, right? You're all like, yeah, of course it can do it, right? Well, there were times when the machines could not do it, right? A human was much better at certain computations than a machine, right? And there are still technical questions you can ask that a human will do in seconds, immediately and in a very well, very good manner, and a machine will have trouble doing it, right? And these are simple stuff like picking this and placing it very gently on the table. Walking. You might have seen the Boston Dynamics robot that walks, right? But that is kind of the exception, and it still cannot do it perfectly. But yeah, think about more questions for your Turing test. So what is artificial intelligence, right? That gives us the idea that if we do have a machine that thinks, we get essentially an intelligence that is artificial, right? And it is a field of computer science and technology that focuses on developing systems and software capable of performing tasks that typically require human intelligence. Okay? And within those kind of ideas, we had essentially computation, kind of developed by Alan Turing out of mathematics. We had information theory by Claude Shannon, which discusses essentially how do we pass on to signals and information between us and between machines, right? So this is discussing, for example, what is a good radio, what is a good walkie-talkie, what is a good television, and so on and so forth, right? But on the level of a very basic signal processing kind of idea. And you have also the idea of cybernetics, developed by Norbert Wiener, and cybernetics discusses the art of controlling machines, controlling a system. And it comes from the Greek word kyverno, which means to govern, to actually make decisions about something. And cybernetics is the analysis of how a system actually works and develops, and how do you make decisions with the feedback that you might get, right? How many of you know how to drive a car? Okay, but the rest also know how cars work, yeah? You press on a pedal, right? So when you press on the pedal, you also get a little bit of feedback. When you press on the brake, you get a force feedback back, yeah? And actually this is, again, first level cybernetics. Second level cybernetics would be the information that passes through a system and to you, right? And also potentially you being part of the system. So it's not just the car, it's the driver and the car that are performing a task together. And that kind of changes how you might need to look at problems. If you look, for example, at a society that doesn't have water, don't look only at the particular village. The problem, where you define the system might be bigger. And potentially that's what you need to develop now in your research. So all these three fields drove the question, can we construct an electronic brain? Okay? And what that might be. So we're discussing essentially machine learning. At the current moment, we're talking about deep learning and predictive analytics. Have you ever used maps on your mobile phone? You say, I want to go there. And the phone actually tells you, you're going to arrive in this amount of time. And most of the time, it is by seconds accurate, right? Or when you're in traffic, can anybody answer me this question? How does Google, for example, know if you're in traffic that there is a traffic jam in one of the bridges that you're going to cross? How do they know? Exactly. Everybody uses their phone, right? So a beautiful example of this is an artist who created fake traffic jams. He took a wheelbarrow and put inside hundreds of mobile phones and started going on a street, right? And what did Google see? Google saw massive amounts of cars, yeah, and then people started not going around that area, right? So that's the level of thinking. You don't need to understand the algorithm exactly how it works, but you understand first principles, right? And that's the kind of level where you need to go, I can design a system that kind of simulates traffic jams. Well, we can debate whether this is useful or not, but yeah. So that's a case of predictive analytics, right? Computer vision. How many of you log on with your face on the phone? Yeah, almost everyone. But also can be used to deter crime, right? We have CCTV, now closed circuit television that can recognize faces. It can go, yeah, that's the thief over there. And image recognition, right? This is a cat, this is a dog, this is a car. A lot of the image recognition and computer vision is used in autonomous vehicles, so driving. Why? Because you need the car to recognize whether something is a hazard or a huge risk of life. So if they're about to run someone over, the car needs to actually recognize this and drive somewhere else or stop. Yeah? When you're doing the captcha on the web and says, click on the hydrants, do you know what you're doing? When you click on the images, say, pick all of the images of the bicycle so that you log in. Do you know what actually is happening on the background? You're actually training a machine learning algorithm because half the images are fake. So what they're doing is they're generating fake, they're doing two things. First of all, they're trying to see whether you're a human or not. And half of it is checking your mouse. Because no human is actually having a stable mouse cursor. Yeah. The second thing they're doing is they're checking if you click on images, whether you can recognize the fake hydrant or not. And from that point of view, they can train essentially their machine learning algorithm to create better images or recognize them better. Yeah. And that's actually how machine learning is trained. Speech recognition. Set a timer for 10 minutes. Done. Yeah. I haven't tried it in Greek actually, so I should at some point. Let me cancel this so we don't get an annoying. And robotics, right? Developing essentially a system that can autonomously operate, walk, save someone from the rubble of a collapsed building, and so on and so forth. And natural language processing, translation, information extraction, right? Give you a text and the machine tells you this is what the text is about. So these are all tasks that are classified under artificial intelligence on a very basic level. Now, the modern kind of idea for artificial intelligence began in 1956 with a workshop in Dartmouth. And the main people there, so this is in the United States, and they created a Dartmouth Summer Research Project on artificial intelligence. Marvin Minsky, one of the kind of biggest proponents of machine learning, along with Claude Shannon from information science, and some of the other scientists kind of gathered and developed ideas about how we could develop artificial intelligence. And from there, we had essentially the first chatbot was created with Eliza. In 1966, we had a lot of criticism and failures. So what happened is that people collectively kind of decided not to fund any more artificial intelligence from 1966 and onwards, because a lot of the promises that were made were not delivered as fast as possible, right? The other thing that happened is that a lot of the science on that era was developed for military purposes, and the main kind of superpowers of the era, the United States and the Soviet Union, funneled their finance into other areas of human science. Okay, so from that point of view, it wasn't a kind of steady development of artificial intelligence. But we arrive in 1997, where Deep Blue is the first machine that wins against a chess champion, won against Garry Kasparov. And at least for my generation, that was kind of like the tipping point where we started having a discussion about artificial intelligence in the normal press and television, right? Up until then, it was discussed mainly in universities and research centers, but not on an everyday life. In 2002, iRobot launches Roomba, the first autonomous vacuum that avoids obstacles. iRobot is one of the biggest companies doing that. Only 30% of the revenue comes from automatic robots and vacuum cleaners in the house of domestic nature. Do you know what iRobot actually does for the rest of the 70%? Can you guess? What kind of robots?
Collect data?
Collect data? No. They don't need to. Military robots. So they're building robots and autonomous vehicles essentially for the military, right? An example of this, one of the most successful models, is a robot for deactivating explosives. Okay? So you see, that's a company that was developing this really great military technology and then transformed also part of it into a very innocuous, very peaceful, and actually a very good piece of technology, right? Having another technology that kind of makes your life easy is a great kind of idea, right? Can you give me another example of a machine at home that makes our life easy?
Laundry?
Very good. The washing machine has done more for the economy and for our well-being than, I don't know, the car or the mobile phone, right? Why?
Because it gives us more time.
Very good. It gives us more time to do whatever we need, and actually gives, most of the time, it gave more time to women because they were tasked most of the time in an unequal manner with washing clothes. Right? If you ever try to actually wash, try it as a joke, right? Try to actually wash your clothes by hand. It's awful, right? And it's going to take you a lot more time, and you're going to waste, time. So, this concept of having a machine that does things for us, right? And it doesn't need to be that smart. Yeah. So, after iRobot, Google built the first autonomous vehicle that operates in urban environments in 2009. So we have essentially, with Waymo, a car that can drive without a driver. In 2011, IBM's Watsons defeats US Jeopardy champions. In 2011 and 2014, personal assistants like Siri and Cortana use speech recognitions to answer questions. And we now have it as a given, right? Like you can talk to your mobile phone. When this started, I was like, and in 2014, we have the idea of the generative adversarial networks, which we'll see later what they are and how they work. A lot of your artificial intelligence machines at the moment use what we call neural networks. So it's a kind of nice way of simulating a brain. And so on and so forth. So I'll speed up a little bit. Now, what types of machine learning do we have now that can help us essentially design? So take it from the point of view, how do I use this now as a tool to design, right? So first of all, we have diffusion models, and these are text to image, right? Create me a nice cabin in the woods with yada, yada, yada. I kind of describe what I want, and I get an image, right? Create a Christian Dior fashion statement if Christian Dior fell in love with Alexander McQueen, right? I was maybe too creative, right? Or you can be very specific, right? I need a red dress with golden details, right? And then it will create an image out of it. And not only it creates one image, but it creates variations on a theme, right? So you can actually ad infinitum kind of create those images again and again and again. Obviously, a lot of times it will create problems, right? It will come up with what we call hallucinations, so things that are not grounded in reality, but are forming part of the data set. So how do we train a model? So if you will hear me talk a lot about artificial intelligence models, right? First of all, what is a model? Can anybody tell me what a model is in this context? Is it a sample? An example. Close enough. It's a driving force. For the design process, maybe. If you're designing and you're making a model of the actual product, what are you doing? It's a prototype, right? It's an abstraction. The model is always an abstraction. It's not the real final thing. It is something that is close enough.
Isn't it? App? Mobile app? It's not actually a mobile app, no. So a lot of the things that we're talking about, so models here is a software piece, a piece of software that is an abstraction of a human mind. Yeah. So from that point of view, a model of a house, for example, if I make a model, right, it's an abstraction of what the real house is. A model of a dress, where I try to model it on a mannequin, is the prototype or the abstraction of what will happen. So here we're talking about a model of a process of how a human mind thinks. So what you do is you take training data, you then wash it through an algorithm. What is an algorithm?
A set of rules.
Set of rules, very good. Those of you that paid attention to my class last week. Or a recipe, yeah? And through that, we instruct the model to learn, and then we get a trained model, right? And that the data that you started with introduces what the model can do, and then we can use it essentially to get results. Okay? That's the kind of general idea. And these models, as very sophisticated levels of mathematics, use essentially statistics. So when we use a diffusion model, or when we use, for example, a general purpose transformer,
most of you know, have used a general purpose transformer under the form of ChatGPT. That's what GPT means. They answer back with the most probable statistically pixel or word that will come next. So the way they are simulating thinking is not by actually thinking, but they run essentially a very advanced statistical engine that will tell them based on the data what is the next probable word that you're going to do. Okay? So they can predict the price of a house based on features such as the size, location, number of bedrooms, or they can actually tell you that's a dog and that's a cat. And you can do that supervised. So I'm taking the data set that you see represented over there, and I'm telling the machine as a human, yes, this is true, no, this is false. That's what supervised machine learning means. And unsupervised, where the machine on its own, by figuring out clusters of information, understands what is what, right? And that is done also by a recipe. So this is a search that Tanya Papasotiriou wrote. How could I quickly identify the trends on autonomous vehicle research? And you might want to do that, right? If you're doing, for example, a solution that drives autonomous vehicles. And she went through 85,587 documents, right? Imagine having to read all of that. Even a whole lifetime you won't be able to do. So it goes through labels, and that filters down to 1,289. And she asked essentially an AI to produce a graph. This is a connectivity graph of how the meaning in the text of those 1,289 was organized. So what do these texts talk about? And again, how could I quickly understand how people interact with autonomous vehicles? So she went on Instagram when you could still actually use the API and search for driverless cars. And then by using more labels, she can actually classify what people think. And potentially, you can use AI algorithms to make sense of any and all of your messy data, right? So it used to be that to train an algorithm, you had to structure the data, you had to put it in order and say, all of these images are images of apples. And even for a human, right? You look at the images and you go, is it a dog? Is it a muffin? Right? Is it an apple? Is it an owl? So artificial intelligence is the ability to imitate human intelligence, and it works with machine learning and algorithms that incorporate intelligence into a system to automatically learn from data. And deep learning is algorithms that mimic the human brain to incorporate intelligence into machines. Okay, so we go from a wider set to a much more smaller. So we're going to take a look at how deep learning works. And now we enter the concept of neural networks, which is essentially creating what we call artificial neurons, right? So all of your neural system and your brain essentially has those structures on the top. This is a neuron, yeah? If you're I'm sending now a signal to lower my hand to my hand, right? And this happens automatically. And it's my brain telling all of my muscles through the neurons what to do. Yeah, it's a decision and then a governance system. And here an artificial neuron is the machine thinking, right? But then you get essentially input signals 1, 2, 3, and then you're going to get actually an output. Some way it will translate all of the inputs into an output. And if we put a lot of them together, and essentially within code, we use mathematics to simulate the inputs and the decision making. You can actually decide on probabilities of certain things.
right? Let's see this in action. How does image recognition work, right? So one of the first ways to do image recognition was on what we call OCR, so optical character recognition, me writing the number 3. And then, essentially, the software is creating that matrix and saying, well, where I get a lead from the pencil, I put a number. And where I don't have it, I put a 0. And then that is fed in all of these neurons that then decide what am I seeing. Do I have a 0 or do I have a 1? And collectively then they will actually recognize the number 3. For some reason my slide is not working. Here you go. And the same thing happens at the level of recognizing an image. Okay, it breaks it down into pixels. And again, we recognize on a very basic level 0 or 1 here. You know, in the category of designing, right, you can recognize whether something is a door or a window or a roof by breaking down an image. Come on. And scanning it. And you see now what happens is that we have essentially 4 algorithms. One is running and recognizing horizontal lines. Another one is recognizing vertical lines. Yeah, someone else is recognizing X's. And then another one is essentially kind of trying to combine the full thing or recognize other features. So what appears a lot of times to our eyes as a very synthetic capability or magic, right, really recognizing, it's actually many smaller machine learning algorithms running in parallel, which when combined can give us essentially a great idea about what's going on with the image we're looking at. And of course, this can take place also on a very, to train this, they take a very clear image and then break it down into much more convoluted networks so that you arrive at unclear images and then you can make decisions out of those as well. And from those point of view, you can use those to find patterns and recognize objects, right? So that's how, for example, your camera on your phone, when it recognizes your face, it uses that kind of idea. That's why, for example, mine is trained before I had the mustache, right? But the mustache doesn't change my facial features, right? But if I put any kind of UV blotting sunglasses, facial recognition doesn't work anymore. Or if I put a mask. Right? So COVID actually wreaked havoc with facial recognition because everybody was wearing a mask, and then Apple and Samsung and Google had to kind of retrain their algorithms to work with masks as well. And here now you can personalize, for example, well, it's important obviously for autonomous driving, but it can also work with personalizing advertising. When you accept cookies in your browser, you allow a set of advertisers to connect things about you and create a profile on you. Come on. And you have also the generative adversarial networks where they use 2 networks. One is creating essentially the output, one input model output, and then you have the adversary, which is telling the first network, yes, this is correct, or that's not correct. So what they're doing is they're using 2 machines. One is learning, and the other one is the corrector, right? If you make a mistake, slap, no, do it again. If you do it fast enough, right, that gun essentially will train the first network to be correct all the time. Okay? And essentially, this is how unsupervised learning happens, right? So the generator is creating a fake sample, and the discriminator is saying, that's the real sample. You compare the two. You tell me what's going on. What is a face? What is not a face, right? And that is the random input vector that the GAN is actually generating. GPTs, right? So large language models. So a general purpose transformer is a case of a large language model. In my opinion, this is autocomplete on steroids. Yeah, and it is actually the same mechanism, right? So autocomplete kind of guesses what character is next, and a large language model guesses what statistically is the most probable character, whereas the large language network does that with words. It appears to you it does it with sentences, but actually the calculation runs for every word, yeah, and will actually drive what comes next. And you can see it here. I start with an A, and then I can go B or C. If I go with B, I could go with O, and that then goes about, above, abyss, ace, or acidic. Yeah, so there is always a tree of decision making that the computer is running what they need to decide on. Diffusion models. This is an artificial generated image of a fireplace designed by Victor Horta. So this is a set of researchers essentially creating the lost notebooks of a very famous interior architect in Belgium. So he destroyed his sketchbooks and his notebooks, and they kind of tried to use artificial intelligence now to recreate what might have been in those notebooks. And the way it works is that they train essentially a model with diffusion images. So you start with this kind of really blurry part that is initially diffused, and then slowly becomes more clarity, right? So then they go, okay, what is the next pixel? What is the next pixel? Until you reach a level where you get absolute clarity on that level. So these are the kind of classic now text to image or image to image generators. I'll show you some examples of how you might, right? I gave to Prom AI an image, and I asked it to go with creating what we call the Vitruvian artificial intelligence, right? So the Vitruvian man is that very famous image depicted normally by Da Vinci, where we have a man standing like that. This was described first by Vitruvius, which is a Roman architect and engineer back in 30 BC. And depending on how I allowed the AI to become more free in the interpretation, right, you will see it started with a very restricted kind of idea, very close to recognize still the Vitruvian man. But on the other side, it went completely on robots in terms of what I drive with the image. So the results might be, well, what I ask it is robotic artificial intelligence depicted as a woman, Leonardo da Vinci style, strong robotic legs and arms like an iron armor. Yeah, very close to the original is the left, diverging from the original is the right, completely off the scale in terms of what it, if I showed you that photograph, you wouldn't say, there, it's very close to Vitruvius, yeah? An image from one of the architects that work a lot with diffusion models. And essentially machine learning using neural nets means that computers can learn the way humans learn. Right? When you're learning language, you observe your parents or everybody around you, understanding that this is an apple, this is a cat, right? And it works the same kind of manner, yeah? And you can create essentially lots of images that are exciting and visually stimulating, but potentially also very bad architecture or very bad design because it's not functional, yeah? So it doesn't mean that because it created an image that it's actually something you should take on board. You can use it, in my opinion, as a very nice interlocutor, say a very nice generator of ideas that you can have a discussion with, right? What if I created a bag or a prototype that looks like this? Excuse me. And you can take that essentially as a point of departure to continue the design process, yeah? And you can also use it a lot in production, right? So you can make a really good sketch, a really bad sketch, and then you can use a diffusion model to kind of beautify it or really make the lines more crisp and so on and so forth. So another part of work from Tanya, right? How can we visualize how the urban street networks will look in the future? Going a little bit more on architecture, right, which is my discipline. Essentially, we're entering an era of working a lot with data integration. And I think it is the same for probably all design disciplines. We have much more data for everything available to us. And we can make better decisions faster, more beautiful, higher, longer, and so on and so forth. But also you see the degree of separation between representation, level of precision, and level of automation, right? So this is a technology that can drive automation, allowing us more time to do our what we need to do. Yeah? Automation is not about doing things cheaper or doing things faster. The absolute goal in the end is gaining us time. Yeah? Well, sometimes you can also do things faster and better. I'll upload this so you can take a look a bit about what are the underlying concepts in design, right? So computational design is very much at the center of it. You also have parametricism and parametric design, so working with defining always a design output as a set of parameters that by changing the parameters, you change the design output. And now totally onto AI. And you can actually map essentially all of this from theory onto models that are data-driven. So on one level, in theory, we ask questions on how, and in practice, we ask questions on what we will do to drive things forward. So opportunities, right? Visualizing ideas instantly. Really simple sketch or model out of a 3D model. And I can jump between where I have it, context, materials, light, integration with the environment, interior, light and architecture, materials again, and context, and so on and so forth, right? Same sketch can give me a multitude of ideas and context with which to work with. Or take me back in time. And of course, again, this is work of Matias del Campo. You can actually evaluate and compare different design options and make informed decisions about what you're doing. So in a group, for example, you could have a prototype and then kind of explore with the diffusion model, what would that look like? Yeah. But also we can simulate and optimize real-time building performance considering factors such as energy, cost, efficiency, comfort, and sustainability. And this applies to all design prototypes. Right? We can build parametric models that take into account all of these things. Whether this is a dress or an accessory or an object or a building, it is the same kind of process. So what you see here is from Infrared City, a company that essentially uses artificial intelligence to simulate wind impact
in urban environments according to your design, right? So you see the architect can move around the model and they can instantly tell you what the effect will be, which used to take hours and days of simulations, right? So now you have it at a 97% accuracy, good enough, I say, in seconds, yeah? We can predict the behavior of materials. So by training an AI on simulation data, we can have essentially instantly on our hands an engineer that will tell us, your solution actually works or it doesn't. But not all can be positive, right? We have some challenges as well. First of all, change can be extremely challenging to people, mostly anybody who is resistant to change. This might be due to cultural background, age, variety of factors that make you resistant to change. And it is very difficult potentially to go from drawing everything on a piece of paper to doing everything not only on a computer, but actually thinking with a computer. So on one end, it can augment us by boosting our creativity in problem-solving challenges. It can help us with a massive amount of work to be done, and can help us also in areas where we're not experts. For example, you might be a design expert and you want to have questions on business models or on entrepreneurial activity, right? And it also you need to always understand what does the data says, what is the context, yeah? Regulations also play an important bit here. What are the laws and requirements of the country you're operating in? And this might not be always the country you're in. So you might be designing for a client in Dubai. What is the law about artificial intelligence in Dubai? Or China, or Latin America, I don't know, or Nigeria, yeah? We live in a global world, and a lot of your designs will not live in the same country you are in. So you always need to understand what happens with the data you're using. Also, a lot of times you will be handling data of your clients. Treat them with absolute religious, let's say, guarding in terms of what happens to that data, yeah? Because they become now a very valuable commodity. And of course, governance. How do we make decisions, and how do we record or understand what was the decision that an AI took? Can I have a record of this? And that is a kind of nice image explaining the Ocean Protocol, which is a kind of blockchain technology that allows us to train AI and understand its governance by using essentially the decentralized ledger technology that is behind blockchain. And it serves also as a nice introduction to our next lecture next week, which is on blockchain. One of the problems with current artificial intelligence is that they rely on a massive, your colleague asked about copying, a massive, essentially, intellectual property stealing, because they go and read and use essentially material that is copyrighted. They generate revenue, money out of that, but they don't give anything back to the original creator, and that is a problem. It is a problem to the fact that even certain AI companies, mostly in the US, actually started lobbying their government to say, you need to change intellectual property, we need to have this. Right? So this raises massive ethical questions of how these things are trained and who owns them and what are they doing with it. And also questions about you, right? You are a designer, you know, intellectual property, the authenticity of your design and your
ideas is what actually is going to sustain you. So these are also to be guarded and protected. Education, what we're doing here, right? I explained to you, you are free to use tools like this, but you need to document how you're using it, and you need to be reflective on telling me what the AI is doing and how are you driving it. Yeah? Ethics and also unconscious embedded bias. One of the problems with AI most of the time in the West is that the people that train AI look like me, middle-aged, white, straight. And that is a problem because I am potentially under increased bias in terms of how I think. So we should actually introduce more diversity in terms of the people who train AI and use it, and so on and so forth. Yeah, and I think that is a big. You always need to understand what potentially is an unconscious bias embedded within the data set, or what the AI is doing. And we have also problems with jobs. Some jobs we expect will disappear because they will be automated, right? So washing your own clothes, in most developed countries has disappeared out of the equation. When I started working as an architect many years ago, there was a job of being essentially a draftsperson. So you would draw drawings for an architect, right? That is now gone. It doesn't exist. It has been replaced with a similar job, which is what we call CAD monkeys. But a lot of times it's actually junior architects or junior designers doing the same work, yeah, for another person. So either the job goes away and you need to kind of retrain that personnel, retrain them and update their knowledge, or you need to find another societal solution, right? Because we were talking about sustainable development, economic sustainable development. You need to make a decision that these people will go and do something else, and it needs to be sustainable for them. Yeah, a lot of the impact actually is not so much on people not your age, but people my age and higher, right? Because it is getting difficult to actually get someone who is 45, 50 years old and say, we're going to retrain you, right? Because you're closer to the end of your career, right? And you're like, why do I need to learn this, right? I'm experienced. But reality is completely different. And always remember that the only constant is change. One of my favorite questions my students ask me is, can you tell me the one software I will learn and then not have to learn anything else for the rest of my life? And the answer is, there is no software you can learn, and you will keep on learning, right? Embrace that and try to follow the constant change. And these are some of the books you can learn, you can read, again, mostly on architecture, but I'll bring also some examples in other areas of design. Thank you so much. And are there any questions?